Imagine you are watching a 6-hour untrimmed home video trying to answer a simple question. Did the person take their medication, and if so, did they drink water right after? In activities of daily living, or ADL, the answer often hinges on a few seconds of subtle visual evidence. A hand reaching for a bottle, a slight shift in posture, a brief overlap of two actions. Traditional short video action recognition doesn't cut it here. You need temporal search, fine-grained visual language reasoning, and the ability to ignore hours of visually redundant background. This is the core challenge of long video question answering, or LVQA. And right now, we are hitting a hard computational wall. Let's look at the math. If you sample a 60-minute video at 1 frame per second, you get 3,600 frames. Feed that into a modern vision language model using a SIGLIP-style encoder at 380 by 380 resolution with a patch size of 14, and you are generating roughly 729 visual tokens per frame. Multiply that out, and you are looking at over 2.6 million visual tokens before you even account for text prompts, timestamps, or output tokens. Hour-long videos simply exceed context windows. They break latency budgets, and they destroy inference costs. You might think, okay, let's just caption the video first. Generate a text summary, run the LLM over the text, and save money. But that approach has a fatal flaw for ADL reasoning. Sparse captions naturally drop temporal grounding, subtle motion cues, and fine-grained hand-object interactions. Once that evidence is lost to text compression, no amount of downstream reasoning can recover it. You end up guessing. The solution isn't to process the whole video, and it isn't to convert it entirely to text. It's to keep visual reasoning, but restrict it strictly to the moments where it actually matters. This is the premise behind TIMEPROVE, a propose then verify framework that splits long video reasoning into lightweight local proposal and expensive targeted verification. The architecture divides cleanly into two stages. The first stage runs entirely on local, edge hardware. It's called the Action-Based Candidate Evidence Module, or ACE. ACE starts by running a single pass over the full video using a lightweight temporal action detector, like MS-Temba paired with a frozen i3D or clip visual backbone. This produces a sparse event timeline, a compact list of what actions occurred and exactly when they occurred. But a raw timeline isn't tied to your question. That's where the query-conditioned proposal generator comes in. An edge LLM, something like Gemma 42B or Qwen 27B, takes the user query and the action timeline and generates candidate answer evidence pairs. Crucially, it does this at two levels of temporal granularity. First, it creates atomic evidence windows that match each detected event exactly. Second, it identifies groups of events that should be considered jointly. For example, if the question asks what action happened while the person was drinking, the LLM will merge the drink window with overlapping or neighboring actions like reading or walking. This two-level strategy preserves precise localization, while allowing the evidence window to expand only when the query demands broader temporal context. Now you have a pool of hypotheses, but sending every single one to a cloud VLM would defeat the purpose. So before any visual data leaves the edge device, TIMEPROVE runs a local scoring and re-ranking engine. This is where the framework gets mathematically rigorous. The ranking function balances 4 distinct criteria. First, temporal compatibility, which biases the score based on query intent like before, after, first, last, or between. Second, semantic relevance, which rewards the strongest action-level match within the window. Third, coverage, which measures how much of the query's core concepts are collectively represented. And fourth, a length penalty that actively discourages unnecessarily long clips. The system sorts the candidates by this composite score, pushing the most promising evidence to the top. This brings us to the second stage, the temporal verifier. Now and only now does the system invoke an expensive cloud VLM. It extracts the top-ranked short RGB clip, feeds it to the VLM along with the query and candidate answer, and asks a single question: is there sufficient visual evidence here? The verifier returns a binary confidence signal, a refined answer, and semantic evidence extracted directly from the frames. If it's confident, TIMEPROVE returns the final answer, the semantic explanation, and the actual video clip as visual proof. If it rejects the hypothesis, the system moves to the next candidate in the ranked list. This continues until an answer is verified, or a predefined verification budget is exhausted. This propose then verify paradigm isn't just efficient, it requires better benchmarks to evaluate it properly. Existing LVQA datasets heavily favor multiple choice formats, where answer options implicitly guide evidence selection. They also rarely evaluate whether a model actually localized the supporting evidence. To fix this, the authors introduced OPENTSUBENCH, or OTB. Built on the Toyota SmartHome untrimmed dataset, OTB contains over 3,500 open-ended questions across 185 untrimmed ADL videos, averaging 21 minutes each. Every question is paired with precise ground truth temporal intervals. The benchmark is stratified into 5 reasoning categories: temporal positioning, long horizon sparse evidence linking, object-centric action identification, compositional simultaneous actions, and state transition recognition. The results on OTB are striking. TIMEPROVE outperforms the strongest existing baseline by 7.3%. But the real story is in the efficiency metrics. The framework reduces VLM invocations by 75% and slashes overall inference cost by 93%. Ablation studies confirm that every component matters. Removing the action detector drops performance significantly, proving that grounding evidence in a learned temporal structure is essential. Adding the edge LLM and the local scoring function provides further gains, showing that heuristic-guided structuring of candidates before cloud verification is what actually unlocks accuracy. The framework also generalizes beyond question answering. When paired with stronger temporal localization backbones like TimeSuite or TimeR1, ACE acts as a reusable query-conditioned evidence selection layer, pushing state-of-the-art performance on the Charade's SDA temporal grounding benchmark. It even shows robustness to imperfect action priors. When boundary noise or label corruption is introduced to the local timeline, performance degrades gracefully because the final prediction still relies on visual verification, not just local labels. Of course, the approach has boundaries. TIMEPROVE assumes that answer-relevant evidence can be captured by a small number of localized or merged action windows. Questions requiring diffuse scene understanding across very long intervals may still need broader evidence aggregation. And like any hybrid system, the final accuracy is still bounded by the visual reasoning capability of the chosen cloud verifier. But these are clear paths for future work, not fundamental flaws. What TIMEPROVE demonstrates is a necessary shift in how we architect long video AI. We don't need to force hour-long videos through a single monolithic context window. By separating lightweight local proposal generation from expensive targeted verification, we preserve fine-grained visual evidence, respect computational budgets, and maintain rigorous temporal grounding. It's a blueprint for scalable, real-world video reasoning. If you want to dig into the architecture, see the exact scoring formulations, or explore the OTB benchmark construction pipeline,